Talk about support vector machines. These things are amazing. And I'm trying to make that big on the screen. There we are. Okay, so here's what happens. You have some data. You have X and Y, and you've got, say, blue things and yellow things. You're trying to separate them. So if you wanted to separate the blue things from the yellow things, you can just have a line, and the things below the line are yellow, and the things above the line are blue. And a whole bunch of lines will work. A line, shallow line like this would work. A steep line like that would work. All of them will have 100% success in separating them. So what's the best line to use? And the answer, which is kind of obvious, is you choose the line that makes the widest road to get the largest separation between the two. That would seem to really be the best way to separate, the most likely to generalize to the population from which these samples were drawn. And the amazing thing about that is the location tilt, the tilt of this line and location is determined only by the points that touch it. The point here and the point there, that's all you need. All the rest of these points do not contribute at all to the location of the best line. As long as they're on this side, it doesn't matter where they are. You could move them anywhere and it wouldn't matter. The only thing that matters is the ones that touch the road. That's why they call it support vector machines. You separate the two with a straight line, and the vectors on the edge are called the support vectors. And just those locations determine the best path. So as you can see, it's computationally very fast to solve. This turns out to be extremely powerful, useful for a lot of machine learning problems, as long as you can somehow turn the graph into something where a straight line will work. And you can usually do that by plotting one axis in log, or squaring a number, or taking the square root of a number. You can usually transform the coordinates. So many problems boil down to just drawing a straight line. Let me make sure I'm recording this. I am. Good. All right. So that's what a support vector machine is. And now we can make them. Let me get my Google Colab up, which is Opera is what I'm using for that. All right. And it may remember, or maybe it's going to make me sign in again. Likes to make me sign in a lot. All right. Okay, there, so here's a place I can put code. Now, so we're going to start with a data set here, and what we're going to do is just make a synthetic data set with some dots in a line just to make a symbolic data set so we can work with it easily. So that will create my instance. They allocate to me some processor and memory. Then it'll run that code, and it's going to make 100 training set samples and 25 test set samples, and it's just going to create them by randomly placing things from a Gaussian distribution, I think. So, still connecting. All right, now it's running. Okay, shouldn't take long. Okay, so it had to download SecML, security machine learning library. And now after it's installed it, then it can run on a thing here that creates this synthetic data. That's the installation. This only has to happen once. There we are. Okay, so now it's created some synthetic data. So you can see this is the right kind of data. For the simplest case of support vector machines, you want to have complete separation between them. And you can see here, the blues are all in one side and the reds are in the other, so I could draw a line through here and separate them. And again, there are various lines I could draw through. But I want to get the one with the widest road separating them. That's considered the best. So now we create and train a model. I make a classifier, support vector machine. A classifier is something that sorts the data into groups. It's just going to sort it into red and blue. And support vector machine is the type of classifier. So then it's going to fit it by just doing it, and then compute predictions on the test set and just give it a rating for how accurate it is. And then it's going to plot it showing the decision boundary, which is how you can easily see what the solution looks like. So there we go. And it didn't take long at all for it to solve, because it doesn't have to go through a lot of iterative steps or anything. It just has to place these things. And so here's what it regards as the best solution, just depending on these two dots and ignoring all the rest. And as you can see, it of course has 100% success on the test set, on the training set, and also on the test set. The original 100 dots and another 25 dots created out of the same population, it correctly solves them. So Now you can try something. This is a real important issue, and I mentioned it last week when we talked about the scale of your data for machine learning. I'm going to expand the y scale. So all I do is multiply the y's by 100. Now when you plot it, it looks the same, but this scale is going up by hundreds, where this scale is going up by ones. So it's the same data, just measured in different units. And so if you were to do a machine learning model, you would expect to get the same model, but you don't, not at all. Here's the same process as before, creating a simple support vector machine model and training it to separate that data. And the result is you get a very different solution, much flatter. And the reason you did is because when you let the scale be this way, what you're telling the model is that vertical distances are 100 times more important than horizontal distances. It tries to minimize the squared error, and the vertical distance is much more important. So now it's got to come very, very close vertically, and it doesn't mind missing by a lot horizontally. So that is what happens. That's why I say you do have to think about the scale of your data in machine learning, because all the numbers matter and the relative size of them matters. So if you just feed in raw data, you measure somewhere like something's in dollars, something else is in square feet, something else is counting population. The fact that they're all at different scales is going to bias your model. So you have to usually normalize everything to go from like 0 to 1 or something if you want to weight all those parameters equally. And that's something you have to adjust with human intelligence. How much should you weight all those parameters? So, all right, and so here's a flag defined there, and now we can move into a more realistic situation. We've been solving a problem that is trivial to solve, which is separating things that have 100% clear separation between them, and that's, of course, you don't need machine learning for that. That's too easy a problem. A more realistic problem is where the data set overlaps. So I'm going to, I'll just keep making new blocks of code. I guess it doesn't matter. So this is just another one with a greater randomness. So now you see the reds are up here and the blues are down there, but they overlap. So now you can't determine the support vector machine by the process I talked about, making the road as wide as possible. You have to have a generalization of it where you allow some errors and you try to minimize the errors. And that does exist. So you can make a model here where it's going to do the best it can to separate those with a straight line. And we'll see how it works. Yep. So there you go. Now in this case, what you're going to do, this is something that happens with all machine learning models. You add a regularization parameter called C. So instead of just minimizing the difference between them, you have another parameter which smooths it out. And C, see if I have any explanation here about C. Yeah, C is a smoothing parameter, which tries to prevent it from being a wild solution, and they usually don't know what scale to use. So if you make it very small, it puts everything in the blue category, which is terrible. But as you make it bigger, it starts being more reasonable. And by the time you get up to 0.01, it's doing a pretty good job of finding what looks like a pretty good path to draw through those dots. And here's 0.1, which seems to result in the same thing. So that's the game, and you can weight them, and here's 1. So there's a wide range of this regularization parameter that lead to similar models that are all pretty good. And you can see the accuracy on the test set is now only 95%. You're not getting 100% success anymore because clearly the data do overlap, and you're never going to get 100% success by drawing a line and separating them. So that's a more realistic case dealing with other problems and that you're going to find. And now we can try to fit data that cannot be separated by a straight line. So let's set this up. This is the moons data set, a common one to test it on. You see make moons. They give you a function just to make moon-shaped data like this, where you have a curve of blue and a curve of green, and you want to separate them. So if you try to separate them with the support vector machine, this one is going to use a linear support vector machine, but it's going to add polynomial features. So what it's going to do is, let me run it, and we'll talk about how it works. All right. What it's going to, this makes a pipeline. It's going to not only take X and Y here, x1 and x2. It's going to also consider x1 squared and x1 cubed and x2 squared and x2 cubed. So it's going to be a higher dimensional space, and it's going to be able to fit more complicated shapes than a straight line when projected down to this two-dimensional space. And that's what I was saying. Almost any problem can be turned into a straight line in a type of graph paper. By adding these other features, that becomes possible. So now we can show the decision boundary of this one. All right. So there. Now you can make a curve like that. This is in fact a straight line in a high dimensional space, including squares and cubes. So it's ax cubed plus bx squared plus cx and the same, but now you can fit a curve like that, which is what you need for this kind of job. And it's still a support vector machine. That's why straight lines are a lot more powerful than you would immediately assume they're going to be. All right, and then you can fit it with second degree, and there's some trick called polynomial kernels, which are a way to do this faster computationally. I didn't really quite understand them, but the result is you can get to basically the same place with much less computation. Instead of actually calculating all the square and cube and fitting the high dimensional space, there's a way to sort of shortcut that. Anyway, so that's what I wanted to show you about support vector machines, a real simple and real powerful model. So let me stop this recording.